Okay, so today we're going to look at another example of determining equilibrium compositions. Specifically, this problem is one of the simplified problems where we have the amount of the starting reagents being the same value, and we're going to look at how that simplifies things. So in this particular question, we're going to look at the equilibrium of bromine gas with chlorine gas forming bromine chloride gas, and the question says that when these two gases react, they form an equilibrium mixture with bromine chloride, and the Kc is 58. And then what the question asks us to do is to calculate the equilibrium concentration of BrCl gas if the reaction started with 0.25 moles each of bromine and chloride in a 2-liter vessel. So to start, we always do the same thing. We're going to write down our equilibrium expression. So K in this case is going to equal our concentration of the BrCl, which is our product, and we're going to square that since it has a 2 coefficient. And then we're going to have Br2 and Cl2 on the bottom. That's going to be our equilibrium expression. Now, the other thing I like to do too is to sort of work out what's given in the question. So this tells us that our concentration of Br2 and our concentration of Cl2, they're going to be the same. And these are initials because the key word here is started. So these are going to equal 0.25 moles divided by 2.0 liters, which is going to be 0.125 molar. And remember, there's only going to be 2 sig figs in that number. So that sort of gives us a starting point. Now, the next step is going to be to set up the ice table. The ice table is important because it's going to allow us to go from the initial concentrations to the concentrations at equilibrium. So to set up the ice table, we write our reagents, bromine, chlorine, and bromium chloride on top, and then we write our I, C, and E. And we're going to put our initial concentrations of 0.125 molar, 0.125 molar, and 0 molar. We write 0 molar because the reaction starts out with no bromine chloride. And then we're going to say, well, this is going to go away, and this is going to go away. We know from the stoichiometry that those are going to be 1s. And here, for every one of these, each of these we get rid of, we're going to make 2 of those. So now we can write our equilibrium expression, which is going to be 0.125 molar minus X, 0.125 molar minus X, and 2X. So now we're going to come back to our equilibrium expression. We're going to plug all this in. So 58 is going to equal our BrCl, which is going to be 2X, and we're going to square that. And on the bottom, we're going to plug in for Br2 and Cl2. Well, this is going to be 0.125 molar minus X and 0.125 molar minus X. So here's where the benefit of having the same concentrations comes in. So now we can see that this is squared up here, and really, since we have this times this and these are the same terms, we can simplify this a little bit and say that, well, this 58 is going to equal 2x squared divided by 0.125 molar minus x squared. So now what we can do is we can simplify this by saying, well, if this is a square and this is a square, if we take the square root of both sides, we can now simplify the answer down and get rid of those squares, and now we don't have to do the quadratic equation. So if we take the square root of 58 on our calculator, you should get 7.62, which is going to equal, and again, 2 sig figs here, so we'll keep track of those, which is going to equal 2x divided by 0.125 molar minus x. And remember, we have to, with a square like this, we have to take both the positive and the negative roots. So what that means is what we have to do is when we're computing this, we have to set one of these up with a plus 7.62 and one of those up with a minus 7.62. So we're going to solve for the roots. And to do that, we're going to have to put a plus or a minus there. So let's do both of those. We're going to set those up. So we have, in one case, we're going to have positive 7.62 is going to equal 2x divided by 0.125 molar minus x. That's going to be right there. And we're going to have negative 7.62 is going to equal 2x divided by 0.125 molar minus x. So if you do some algebraic rearrangement, we can say, okay, 7.62 times 0.125. So we're going to get 0.9525 minus 7.62x. What I've done is I've just brought these two terms together and distributed 7.62 into here. So I've cross multiplied. So that's this term brought up is going to equal 2x. Okay, so that's that one. And we can solve for x, just 7.62 x plus 7.62x. That's going to be 9.62x, which is going to equal 0.9525. And if you solve for x by dividing, x is going to equal, in this case, 0.9525 divided by 9.62. That's going to be 0.0990, again, 2 sig figs, carrying that all the way through, molar. So that looks like a good root. This one we're going to do the same thing. So in this case, we're going to get minus 0.9525 plus 7.62x, which is going to equal 2x. So we're going to subtract in this case. So 2 minus 7.62, just so that we get it right. So that's going to be minus 5.62x is going to equal minus 0.9525. So x in this case is going to equal 0.169. Yep. Again, 2 sig figs. So now we're going to sort of assess which of these are our correct roots. So in this case, we can probably look over at our ice table. So I'm going to slide back over here. Our maximum number is 0.125. So this root I think we can exclude already, because if we subtract this from 0.125, we're going to get a negative number. So I'm going to X out this root, and I'm going to say that this must be our root. Okay? So let's bring that up and figure out what the equilibrium concentrations are. So if we want to know the equilibrium concentration of the BRCL, which is what the question asks, we're going to take 2 times our root, which is 0.0990, and this is molar. And we're going to get, so 2 times 0.099, that's going to equal 0.198 molar. So that's going to be our concentration of the BRCL at equilibrium. And then our concentration of BR2 and our concentration of Cl2 at equilibrium is going to equal 0.125 molar minus that 0.0990 molar, which is going to equal 0.026 molar. So that's that concentration, and that's that concentration. So technically, you could just box this answer off right here and say, okay, my answer for the entire problem, probably best to go to do something like this so that I can see it when you're doing it on the exam, is 0.198 molar. And then put a nice big box around that. That should be good enough for me. Even here, I could probably figure it out if you did it cleanly. So that should get you the final answer on the exam. Remember, the question asks for the concentration of BRCL at equilibrium. Now, one thing that's a good way to sort of check everything is to go back to your equilibrium expression and plug everything in. So what should happen, so this is the check now. So if you want to check your answer to make sure everything is right, a good way of doing that is to say, well, okay, let me calculate K with my numbers. So I'm going to plug in our equilibrium concentration, 0.198 molar, and then this is going to be squared. So I'm plugging this into K, and then I'm going to take our 0.026 molar, which is our Br, and our 0.026 molar, which is our Cl. And this should equal something close to 58. So if you plug this into your calculator, 0.198 squared divided by 0.026 squared, you get 57.99. So that checks out. And what should happen here is your equilibrium concentration should equal the K value that you got in the beginning. If that's not the case, then you've done something wrong. So that's a good way of just making sure that your numbers make sense. Because if they don't add up, if they don't multiply out to that K, you've got a problem. So I'm going to post this sheet online. It looks a little bit messy, but it is definitely has the answer on it. If anybody has any questions about this, feel free to shoot me a quick email. Okay, guys, good luck for the exam.